Welcome to class number 14 of transport phenomena in mesoscopic and nanoscopic systems. Now I think we are ready to go into the transport part, but before that let me just specify some other thing. So generally let us say we have a bar of silicon. So this is a silicon bar, and we have doped certain parts of it with donors and acceptors. Okay, so here we have doped it with, let us say, Nd equals to 10 to the power 24 per centimeter cube. Here also we have doped with Nd equals to 10 to the power 24 per centimeter cube, and here let us say that we have kept the acceptor type doping with Na equal to 10 to the power 22 per centimeter cube. Okay, now how would the band diagram look like? So let us first try to understand the physics, that what would happen. Initially, since all these three parts, that is this part, and this part over here, all these three parts are made up of silicon. So their conduction bands would basically lie at the same energy. Okay, so let us say that this is our conduction band, and this is the valence band, the spatial diagram. So this would basically lie at the same energy because all these three are made up of silicon. Okay, this is known as the flat band condition, and this is basically the band diagram when no charge transfer has taken place. Okay, so no charge has flowed from this region to this region or this region to this region. So in that condition, the conduction band of all the three parts, that is this part, and this part, should be aligned with one another because all these three parts are made of silicon and their conduction band should be at the same energy. Okay, now what is different between these three regions is basically the doping concentration. So this is doped with donor type impurities, so its Fermi energy is somewhere close to the conduction band. So let us say that the Fermi energy is somewhere here. So let me draw with a different color. So let us say that the Fermi energy is somewhere here, and then this region is doped with acceptor type impurity, so its Fermi energy would be closer to the valence band. So let us say that the Fermi energy for this region is somewhere here, and then for this region again the Fermi energy would be closer to the conduction band over here. So their Fermi energies are different, and when the Fermi energies of these three regions are different, it basically dictates that electrons would flow from one point to another. Okay, because Fermi energy has to be same throughout the entire device in equilibrium. So whenever the Fermi energies are different, this basically means that the electrons would flow from one zone to another. Why? Because here in this in this left region and in this right region over here, the probability of occupancy of electrons at the higher energies is basically more, and that is why these electrons would try to flow from this region to this region and from this region to this region, because in the middle region the probability of occupancy of electrons at higher energy is lesser. Okay, that's the crude explanation. So now electrons would start flow from here to here and from here to here, and you can also say that holes would start to flow from here to here, but we are not worried about holes right now. We would just discuss the electronic part, and once you understand the electronic part, the whole part would also become clear. Okay, so now electrons would flow from here to here and from here to here. So what will happen is that a positive charge would basically build up in this region, a positive charge would build up in this region at the interface because electron has flowed out, and a negative charge would build up in this region of the interface because electron has come in from outside. Okay, similar is the case of the second interference to the right over here. And now what would this create? This would basically create an electric field. So an electric field would be created in this direction over here, and this electric field would also be created from here to here because here positive charge and this negative charge are separated in space, and we know that whenever charges are separated in space, it basically creates an electric field. Now what does this electric field do? So this electric field basically changes the potential energy, because whenever there is an electric field and whenever a charged particle moves through an electric field, the potential energy would basically change. Okay, and the change in potential energy is basically proportional delta U. The change in potential energy is basically proportional. So let me write it in a different language. So the change in potential energy between x1 to x2 is basically equal to minus the integral of E dot dx between x1 and x2. Okay, so basically the potential energy basically changes opposite to the direction of the electric field because there is a negative sign here. Let me reframe the statement. So the potential energy basically increases opposite to the direction of the electric field because there is a negative sign over here. Okay, this is not the potential energy, but this is the potential actually, the change in potential, that is. So if we talk about the potential energy, we basically have to multiply this by the charge. Okay, the charge times the change in potential is basically the change in potential energy. So if we want to calculate the change in potential energy between x1 and x2, then we have to basically multiply the change in potential by the charge, and electrons have a negative charge. So let me repeat the statement again. So the potential basically increases opposite to the direction of the electric field, and electrons have a negative charge, so electron potential energy is supposed to increase in the direction of the electric field. Okay, so now we know that this potential energy of the electrons would basically increase in the direction of the electric field. Now what is this conduction band EC, this conduction band H? What is this conduction band H over here? So this, in very layman's terms, we can say that is the potential energy of the conduction band. Okay, so any electron that resides in the conduction band must have this potential energy equal to the band edge, and then the rest of the energy is basically kinetic energy. So if an electron resides at this location in the band and has an energy E, then EC is basically the potential energy of the electrons in a very simple crude language, and then this energy, which is the difference between the total energy and this band edge EC, this is basically the kinetic energy of the electrons. Okay, so EC can be said to be the potential energy of the electrons in the conduction band. Okay, now we just said that the potential energy of the electrons is supposed to increase in the direction of the electric field. So how would the potential energy of the electrons increase? So let me use a different color over here. So here there is no electric field, and here there is no electric field, and here also there is no electric field. So the bands would remain flat in these three regions. And then in this region and in this region there is electric field, so the bands would basically bend and the bands would increase in the direction of the electric field. So it increases like this, remains flat, and then it decreases again. Okay, so for valence band also it is basically the same. So now, is this thing important for electronic transport, or let us say, would this phenomena, so this blue line is basically the spatial band diagram of this device configuration over here. Now, is this configuration, or is this pattern of the band diagram, is it important for electronic flow? Of course, yes, because if an electron basically resides at this energy over here, then it would basically travel and it would strike this hill-like top over here, and there is no electronic states in this region. Okay, because this region lies in the band gap. Okay, this entire region lies in the band gap, so there is no electronic state in this region. Okay, so if this region is thick enough, in that case the electron would flow, it would collide with this potential barrier over here. So this hill-like structure we call it the potential barrier. Okay, so this electron would flow, it would basically collide with this potential barrier, and then it would get reflected back, so it would travel back like this. Okay, but an electron which is here, this will basically flow, because its energy is greater than the energy of this barrier or this barrier height, so it would basically flow to the other side. So it is basically important, the point that I am trying to make is that it is basically important to know this barrier height and the overall structure of this barrier. For example, if this barrier is very thin, if this thickness is very small, then an electron can actually flow, it can collide with this barrier, and then a part of this electron would get reflected back, and a part would basically travel through this band gap and reach the other side. So this phenomena is basically known as tunneling, where an electron can flow to a very small distance in a region where or through a region which does not contain any valid electronic state. Okay, this phenomena is known as tunneling. So the point I am trying to make is that it is important to know the structure of the barrier, or how this spatial band diagram looks like, if we want to solve the characteristics or the current flow or anything inside the device. Now, how do you know that what is the structure of this barrier? So you might say that there are formulas for depletion region, and this region is basically the depletion region, and you might basically say that there are formulas for depletion region, and we can basically know from that, and blah blah. But there are limitations when it comes to semi-analytical formulas as far as the case of devices are concerned. The issues are that it contains a number of approximations. For example, when you write the formulas of the depletion region inside the p-n junction, what kind of assumptions do you make? You assume that it is an abrupt junction, so the depletion region ends suddenly. Okay, the second assumption that you make is that all the carriers inside the depletion region is gone, the depletion region is totally depleted, and then suddenly after the depletion region ends, the carrier concentration suddenly increases, okay, to Na or Nd. So these are some crude approximation which we make, and of course it kind of gives us close enough result in some cases, but in some cases or in many cases it doesn't. So it is actually important to solve this pattern, or to solve this spatial band structure numerically when you are doing a electronic transport calculation. Okay, instead of just looking at the formulas and predicting how things look, it is important to basically solve this barrier structure over here, or this spatial band profile over here. And this is exactly the thing which most of the device simulators like Centaura, Silvaco, they basically do this. They solve numerically this band structure and then they solve the device characteristics. So now there is a problem over here. So the first problem is that how do you solve this characteristics? So remember that what is the reason, remember that the reason that this hill like structure was created over here, the reason is basically this charge accumulation in this region and charge accumulation in this region over here. Okay, so to solve this hill like band structure, spatial band structure, you need to know about the charge concentration in this region and this region. This is obvious. So if you have the charge concentration in these two regions, you can directly solve this spatial band profile by using Poisson's equation. Okay, so let me write it here. So Poisson's equation, and this Poisson's equation, what does it tell? So this is a function of R, so let me just write it here. This is a dot product actually. So U is basically the spatial potential, so we can write it as U of R equal to minus rho at this point R divided by epsilon 0. So right now we are considering electrons only. So if you have holes along with it, so you have to basically add that also. So we will be considering electrons only just for simplicity. So this is equal to Q. So electrons have a charge minus Q. So this minus goes out of picture. So this is equal to Q in R minus N0 divided by epsilon naught. So Nr is basically the electron concentration at point R due to transfer of charges. So just as I said that this electrons would flow from here to here, so that is why the total electron concentration would change. So Nr is the total electron concentration, and N0 was basically the initial electron concentration that was there when the bands were totally flat. Okay, when no charge transfer took place, then the charge concentration or the electron concentration was N0. Okay, so N0 is basically, we can say that it is almost equivalent to the doping concentration. Okay, this doping concentration over here. Okay, and Nr is basically the total electron concentration when charge transfer has taken place and the device has reached equilibrium. Okay, now if we know this quantity over here, this Nr minus N0, or if we know this Nr and N0, then we can readily compute this spatial potential. But the question is that how do we know this electron concentration in R in space? So the answer is very simple, that to know this electron concentration in R, we just need to know the spatial potential profile. This potential profile we need to know, because if we know that this spatial potential profile is this, and we know the Fermi energy of the system, then in a classical picture, okay, if we use classical mechanics, then we can readily compute this Nr as the integral over energy minus infinity to plus infinity, the density of states at point R and at energy E times F0, assuming that the device is in equilibrium and no voltage has been applied across the device, F0E dE. Okay, if we know this band profile, then we also know this density of states. To know this density of states at point R and at energy E, we need to know this band profile over here. So if we have this band profile, then we can readily compute this NR. So we are now in a loop where to know this band profile, that is to know this UR, we need to know NR, but to know NR we need to know UR. Okay, so we are now in a loop where we basically need to know UR to compute NR, but then to compute this UR we need to know this NR. Okay, so we are in a kind of locked up situation. So what to do here is that we cannot solve for either UR or NR directly, but we need to solve these two self consistently. Okay, because there is a dependence between the two, one depends on the other, then we have to solve it self consistently. Okay, so now when we move back to quantum transport, so in case of quantum transport we cannot really use classical mechanics. We have to know the eigenstates or the allowed states in the system to basically know the electron concentration. So what we do, we have to solve this equation H0 plus U phi psi alpha equals to E alpha psi alpha. This is again I am writing it in a crude way. So H0 is the Hamiltonian of the system before any charge transfer took place, and then when just as we have introduced doping concentration, charge transfer would be there, and so this extra potential U would be created. This is the potential due to the depletion region and due to the charge transfer. So this would also come into picture, and this is the total Hamiltonian of the system H, and then this is a wave function. So we have to solve in a very crude language. We have to solve this Schrodinger's equation H plus U psi equal to E psi, and from here we can basically compute the total electron concentration in R as summation over alpha phi alpha square. So this gives the so I will write it as phi alpha R square over here, R square, then F0 E alpha minus mu. Okay, so why this F0? So remember that this gives us the spatial availability of a state. For example, if we consider this diagram over here, just as I stated, that if this is an energy state, over here, this electron would just flow, it would collide with the barrier, and then it would get reflected in this direction again. Okay, so corresponding to this energy, there are no states in this band gap over here. Okay, so whether there would be a state or not at a point in space, that depends on that point itself. So that is why this psi alpha, this is actually a function of R. For example, if this alpha has the eigenenergy at this energy over here, okay, in that case there are states corresponding to this eigenenergy in this region, but there are no states corresponding to this eigenenergy in this region over here. Okay, so just to make it simple for you, so let me go back to the next page. So this gives the availability of a state in space at any given point in space, and then this term is basically the probability of occupancy of that state. So you have to multiply this availability of state, that is this part over here, by this part over here. Okay, so this gives us the electron concentration. Now this electron concentration, total electron concentration, basically determines what this potential should be. Okay, so so this is actually the electron potential. So let me write it as UE. Okay, so now this NR basically determines our potential UE. So we again go back to Poisson's equation. So del dot epsilon r del ur is equal to minus rho r divided by epsilon naught, which is equal to q in r minus n0 divided by epsilon naught. Okay, and then UE is basically equal to minus q times UE. It should be again a special variable. This is minus q times the potential UR. Okay, so this needs to be solved in a self-consistent loop till convergence is achieved. So we start with an initial guess of this potential, and closer is the guess to the actual case, closer is the convergence. So we start with an initial guess of this part, and then we calculate this eigenstates of the Hamiltonian, and we calculate this total electron concentration. And once we calculate the total electron concentration, we again go back to this formula to calculate this UR over here, and we repeat this step till convergence is basically achieved. Okay, this is how any electron device simulator works. Even Silvaco and Centaurus, which are basically classical level device simulators, they also basically work in this fashion. They basically solve this electron concentration and this potential profile self-consistently. The only difference is that here, in case of classical transport simulator, we do not really solve this equation to get the eigenstates of the system, but we resort to classical formulas, for example density of states, etc., to basically calculate this electron concentration. Okay, so in case of classical simulators, only this step is different, that we do not really solve for the eigenstates of the Schrodinger's equation, but all other steps like this self-consistent loop between calculating the spatial band diagram and the electron concentration, this is basically the same. So this is how any transport simulator would work in a self-consistent manner. And when you basically, if any of you have used Silvaco or Centaurus, in some cases you might have noted that sometimes the simulation fails to converge. Okay, sometimes the simulation fails to converge, and it gives you a convergence error, like Poisson Schrodinger convergence has not been achieved, or Poisson Schrodinger convergence have failed, or some equivalent message like this. So when they say that this convergence has failed, it is generally the convergence of this part of the simulation they are basically talking about. Okay, okay, so just remember that this is the step. So this part basically is the transport simulator. So this is basically the electron transport simulator. Here we have applied this Schrodinger's equation. So this is a quantum transport simulator basically. So I would just write it as electron transport simulator. And this part is basically Poisson solution. Okay, so the entire simulator basically, if you want to construct a simulator either in C or in MATLAB, then you have to basically incorporate this entire part or write code for this whole thing. Okay, and normally quantum transport simulators are not available in any commercial software yet. So if you want to apply quantum transport or if you want to study quantum transport for any device, you really have to write the code yourself in C or MATLAB. Okay. Another thing is that how do you really numerically solve this equation once you have this information on NR, because you have to solve these things on a computer. So there are many methods, but the easiest method is basically to express this operator del dot inverted delta dot inverted delta into a linear operator. In case this epsilon of r, if this is constant or this does not vary with space, then this form basically becomes epsilon r Laplacian of ur, and the easiest method is basically to convert this operator into a matrix. This is a linear operator, so you can easily convert into a matrix, and then this in the numerical technique this gets replaced by a matrix over here, and then we have this minus rho divided by epsilon. So rho is also a matrix in when you are solving it numerically, and then you basically invert this matrix over here and you put this inverse over here to get this value of ur. Okay, so you can follow the details in the book Quantum Transport from Atoms to Transistor, but I just wanted to give you a hint, but the details is given in the book. I will not discuss the details over here because this kind of details you have to learn yourself, and this is the easiest method, but this is not the only method or the most efficient method to compute this ur numerically. There are other more sophisticated methods as well. Okay, so now we'll be starting a formulation which is known as the non-equilibrium Green's function formulation. Which is also known as NEGF. Of course, it would take a few days to cover it up, but let me start by taking a structure where you have a contact. So let me just use a different color. I will mark the atoms in the contact. So we have a 1D contact. We'll just assume the simplest case. Once you understand the simple cases, then it's easy to go into more detail. So we have a 1D contact. We also have a 1D channel. So I'll just mark these atoms in the contact by red. And then I'll mark these atoms in the channel by blue. So let us assume that this contact has m atoms or m number of lattice points, and this channel basically, let us say it has n atoms. So this is a 1D contact, so n points. Okay, Now what we do here is that we first assume that this contact is actually in quasi equilibrium. Okay. Okay, so let us go to the assumptions later because this is not important right now. But let me just start by saying that I know what the Hamiltonian of this channel is. So the channel has a Hamiltonian H. So H is the Hamiltonian of the entire channel, and I have written this Hamiltonian in the form of a matrix. It can be a function as well. The formulation or the method doesn't change, but because we generally solve it numerically, I would assume that this Hamiltonian H is a matrix. Okay. Now this Hamiltonian H basically determines the characteristics of the channel. It contains all information about the band structure, the band profile, and etc. So the characteristics of the current flow through the channel depends on this Hamiltonian. Now another factor also governs the current flow, which is the characteristics of this contact over here. Okay. For example, if the contact does not have electron at a given energy, then at that energy no electron can flow through the channel because the channel would be collecting the electrons from the contact only. Okay. So if corresponding to a particular energy there is no state in the contact, in that case at that energy, even if the channel has some state, at that energy no electron would flow through the channel because no electron is available at the contact at that energy. So this is the simplest case where the contact basically governs how the current flows through the channel, or what is the mechanics of the current flow through the channel. Of course things are more complicated, but I just gave you a simple example to understand. So this contact also has a Hamiltonian of its own, which we call HR, and this Hamiltonian HR basically governs the characteristics of the contact, and the Hamiltonian H governs the characteristics of the channel. Now we will assume that the contact is semi-infinite, that is it basically contains atoms to this direction also, but we will not worry about it here. So HR can be a large matrix. Even if it is not semi-infinite, we would assume that the contact is large. So HR might be a large square matrix, but we are not explicitly, or we are not definitely saying the size of HR, but we just are saying that HR is a large matrix. Okay. So this contact is large, it consists of a large number of atoms. So this channel really does not influence the characteristics of the contact to a large extent because the channel is generally small. Okay, if you have used cadence, you would generally see that when you make the contacts, when you make the layout, or if you have used some layout tool like Magic, when you make the layout, you make the contact really large compared to the device. Okay. And one of the reason is that the contact is basically supposed to drive as much current through the channel as possible when the device is on, and that is only possible when the contact has much larger number of electrons than the channel can ever have. If the contact has much larger number of electrons than the channel can ever have, then the contact is always ready to supply electrons to the channel. Okay. So that is why the contact should be made large. On the other hand, if the contact is small, in that case, let us say if the contact has 10 electrons and the channel can take 6 electrons, then of these 10 electrons, these 6 electrons are gone here, so you are left with 4 electrons. So this contact would wait till the time this 6 vacant electrons, or the 6 electrons which have traveled to the channel, the contact would wait for those electrons to be replenished. Okay, so in that case the contact cannot drive maximum current through the channel because the contact would itself wait for its electrons to get replenished. Okay, on the other hand, if the number of electrons in the contact is very large, then the contact can drive maximum current through the channel. The contact always has electrons to supply to the channel. Okay, so that is why the contact is generally made large, and this is another way of saying, or another language of saying, that the contact can indeed influence the device. The contact can change the characteristics of the device or the channel, but the channel cannot change the characteristics of the contact because the contact is large. For example, when you dope silicon with phosphorus, if the concentration of phosphorus is small enough, then the entire device or the entire doped semiconductor would have the characteristics of silicon. Okay, but if you mix silicon and phosphorus with 50% concentration, so 50% concentration of silicon and 50% concentration of phosphorus, then that kind of material would have the characteristics of both silicon and phosphorus, because the phosphorus is now a large concentration of the material. But if you dope silicon with 1% phosphorus, which means that 1 in 100 parts of the material is phosphorus and the 99% of that material is silicon, then that material would have the characteristics of silicon. Similarly, here also, if the contact is very large compared to the channel, or if the contact contains much larger number of atoms compared to the channel, or much larger number of electrons compared to the channel, in that case the contact can influence the characteristics of the device or the channel, but the channel cannot influence the characteristics of the contact. Okay, so let me write it here. And this is the assumption for all of the device simulators, and this is also how in reality contacts are made. And in reality, the reason for making the contacts as large as possible is that they can drive the maximum current through the device, or as much as current through the device as possible, so that you can harness the maximum potential of the device basically, or the channel. Okay, and it's a active and hot area of research to make suitable contacts actually. Okay, right now there is tremendous efforts in or tremendous research to basically develop good contacts. Okay, there is process research, there is materials based research to basically make good contacts for channels, because that when you go towards the nano domain, this contact to channel interface basically forms the bottleneck of how much current can be driven through the channel. So if the contact is bad, in that case, although the channel might have ideal properties, the channel would not be able to drive much current. On the other hand, if the contact is good, then you can really exploit the full potential of the channel. Okay, so it's not only the channel which is the important part of the device, but when we really go to the nanoscale, then the contact also forms a very important part of the device. Our contact to channel interface also forms a very important part of the entire device. Okay, very important governing part of the entire device. Okay, so contact is large, and contact can influence the device channel or the channel, but channel can't influence the contact. This is point number 1. And point number 2 is basically, since these contacts are large, contacts are always in quasi-equilibrium. We will see why the second point is important later, but why it is in quasi-equilibrium, or why the assumption of quasi-equilibrium contacts is valid, is because the contact is large compared to the device channel. Okay, so the device channel cannot drive the contact to a state which is far from equilibrium. Okay, the device would never draw so many electrons that the contact itself gets far away from equilibrium. Okay, so the contact should always be in quasi equilibrium. Okay. Okay, so now we know that we have a contact and a device 1D channel and a 1D contact, and the device has a Hamiltonian H and this contact itself has a Hamiltonian HR. Remember that this Hamiltonian HR is the Hamiltonian of only this contact when this channel was not interfaced with it. So when this contact was isolated, then HR was the Hamiltonian of this contact. Okay. Similarly, when the channel was isolated from the contact, then H was the Hamiltonian of the isolated channel. Now this contact and the channel are joined with each other. So the wave function of this contact would basically spill inside the channel, and then the wave function from this channel would also basically spill inside this contact. So let us assume that this contact wave function is given by this parameter phi, or phi r, let us say. So this is also a matrix. So this HR is basically an m cross m matrix because there are m lattice point. This phi r is basically a vector. This is basically an m cross 1 vector. And this Hamiltonian H, this is basically again an n cross n matrix. And let us say that the wave function inside this channel, this is basically given by a vector psi, which is again a n cross 1 matrix. Now we will basically form separate units. Let us assume that this channel is a separate unit, and then this contact is basically another separate unit. So we are doing this similar to the case where similar to the case which we did for the 1D chain of atoms with dimer unit. So I will just quickly go back to that page to just make you recall. So here we took 1 unit to be each dimer, and we had this units inside the matrices, which are again smaller matrices basically. So this matrix denoted the coupling between the second unit and the first unit. This was the coupling between the second unit to itself, and this was the coupling with the second unit to the third unit. Okay, so if we define units here in case of the dimer, we have sub matrices within the matrix which define the coupling of one unit to another. Okay, so here also just as that case, we are taking this contact as one unit and the channel to be one unit. And so and let us say that the coupling between this channel the coupling between the contact and the channel is basically denoted by this matrix tau. Okay. So this denotes the coupling between channel and contact, or I should not say coupling between channel and contact, because this matrix, let us define that this matrix as how the channel is basically coupled to the contact. Okay, how the channel is coupled to the contact. So how the contact is coupled to channel, that is basically denoted by the matrix tau dagger, which is the conjugate transpose of this matrix tau. Okay. Okay. So we write the equations here. So let us say that E is the eigenenergy of this entire system. Then we have E psi. Psi is basically the wave function inside the channel here, and phi is basically the wave function inside this contact. This is equal to H. So earlier when this channel was isolated from the contact, then the equation just used to be E1 psi equals to H psi. Okay, E1 psi 1 equal to H psi 1. Okay, now this channel is coupled to this contact, so the wave, so this equation is H psi, and then this contact wave function also comes inside the channel, so the channel is coupled to the contact, so tau phi. Okay, similarly, if the contact is coupled to the channel, similarly the channel if the channel is coupled to the contact, similarly the contact is also coupled to the channel in a similar way. So this coupling is denoted by this matrix tau dagger, and then we have the original equation for the isolated channel would be E2 phi equals to HR phi. So we have this HR over here. So this is the matrix of the entire system. This is basically, as I stated, this is n cross n. This one is basically n cross m. So this matrix tau basically defines how these n atoms inside the channel are coupled to m atoms inside the contact. So basically the first row of this matrix defines how this atom is coupled to all other contact atoms. The second row of this matrix tau defines how this second atom is coupled to all other contact atoms over here. So basically like that. So this is a n cross m matrix. Okay. Similarly, this tau dagger, this one is basically a m cross n matrix, and this Hamiltonian HR, this is basically an m cross m matrix. Okay, so this is kind of equivalent to Schrodinger's equation for the entire system consisting of the contact atoms and the channel atoms. Now remember that we could of course could have solved this equation if we would have accurate information on this Hamiltonian HR, but the issue is that, just as I stated, that the contact is large and typically it should be semi-infinite. So this Hamiltonian HR is also a very large matrix. Okay, because M is typically very large. Okay, so if HR is very large, it basically makes this entire matrix very large, and then it becomes a computational trouble or computationally intensive to solve this entire matrix. And remember that it is not sufficient to solve this entire equation once, because we also have to solve the Poisson's equation self-consistently along with it. So we have to solve this entire equation repeatedly, or this kind of equation. I should not say exactly this equation, but we have to solve this kind of equation repeatedly till the convergence is achieved, and this becomes a huge trouble in case of computational tasks. Okay, or when this is solved numerically. So what our intention is basically to remove this matrix HR by some equilibrium statistics of the reservoir. So what is the equilibrium statistics of the reservoir? So we have so let me write it here. So since the matrix HR is very large, our intention is to replace HR by some equilibrium statistics of the reservoir. So what is the equilibrium statistics of the reservoir? So we have when the reservoir is in equilibrium, we have information on the Fermi energy. So we also, not equilibrium, but when the reservoir is also in quasi-equilibrium, we have information on the Fermi energy. If we have information on the Fermi energy, we also have information on the electron distribution over energy. Okay, so we have that information. The second information we have is the dispersion relation or the EK relation. So these are the parameters, or these are the information with which we intend to replace the action of this reservoir HR. Okay, because what information does this matrix HR basically gives us? If we ask ourselves that what information does this matrix HR basically gives us? So this matrix HR basically gives us information on the states. So HR basically gives us information on states and also information on energy. So remember that when we solved the case of 1D potential well, we had information on the K states, we also had information on the allowed energies. Okay, so it gives us information on states, we have information on the energy and the relation between these states and energy. Okay, so I will just put an arrow over here to denote that it also denotes information between states and energy. And when we have all the three, or let us write it here. Information on EK relation, let us write it, EK relation. When we have all the three, we can basically know the information about the density of states. Actually, this information on K states is also given by the boundary conditions, but let's not delve into too much detail. But when we have all the relation HR plus, I will write boundary conditions over here. And when we have all this information, we know information on the density of states. And so we can basically replace this information available in HR by the density of states, by the EK relation, and information on the available energies. Okay, and we will see next day that this information on this matrix HR can actually be replaced by defining a matrix sigma where we have only this equation E psi equals to H plus sigma psi plus S. So this S basically depends on the contact, and this sigma also basically depends on the contact. So by defining these two matrices sigma and S, we basically have omitted, or we basically have made the calculation simpler by reducing this entire equation to a set of this entire equations, or this entire matrix size, to a smaller matrix size which has n cross n elements. Okay, this one is n cross 1, this one is also n cross 1. So we have basically reduced our computational burden. Okay, so let us do up to here today. Thank you everyone.